Hello guys, in this part 2 GIS analysis video lecture I am going to discuss the different types of raster analysis technique that are frequently used by the GIS user. As you know, in the part 1 GIS analysis video lecture I already covered different types of vector analytical capabilities. So let's start. All the different types of raster analysis technique that we will discuss here one by one. Raster data analysis is based on basically cell, or also called pixel, and raster. That totally depends on pixel or cells and depends on the raster. It can be performed at the level of individual cells of a raster, or group of cells of a particular raster, or cells within an entire raster. So different types of raster analysis can perform on raster based on either individual cell or group of cell or the entire cells present within a raster. That means all the cells that are present within raster. So it will vary. Some sort of raster analysis technique only use individual cells of a raster. Some sort of raster analysis technique use group of cells for doing analysis, and some sort of raster analysis technique use all the cells of a particular raster. Some raster data operations use a single raster, and other raster data operations use two or more rasters. So as like the previous one, some sort of raster operation or some sort of raster analysis technique use only single raster, or some raster analysis technique use two or more rasters. Raster data analysis also depends on the type of cell value. That means based on which raster user will perform raster analysis, this cell contain whether numerical value or categorical value like some textual data. So pixel can contain numerical value or categorical value like land use name, like soil type. So that can be present, or maybe cell can contain numerical value like elevation, like rainfall, and so and so. So different types of raster operation also depends on which type of value present within each and every cell. That can be either numerical, or that can be either any categorical value, or more specifically some textual value. So in the next slide I will show you some of the common raster operations that we generally perform using GIS software. One of them is called, we generally perform local raster operations. Second one, we also perform neighborhood raster operations. We also perform zonal operation. Based on certain zone, we also perform raster operation. Based on raster, we can also perform physical distance measurement. Based on raster data, based on specific source or specific sources, we can also perform allocation operation and direction operation, which is very useful for transportation purpose, for suitable site finding purpose. Allocation and direction. So both physical distance allocation and direction raster operations are based on raster along with some sources, either single source or many sources we can use. The next one is there that is called raster generalization operation. just to reclassify or just to generalize a raster, we can also use generalization operation. So those are the common types of raster operation generally we perform using GIS software. So let's start one by one, discuss all such type of raster operation in front of you. So first one is there, local raster operation based on only single raster. When you have only a single raster, based on this raster we can perform local raster operation. Given a single raster as the input, a local operation compute each cell value in the output raster as a mathematical function of the cell value in the input raster. So whatever the raster you have, in this raster every cell has certain value, and based on this raster when you perform local operation and when you create a new raster or output raster where every pixel, every cell in this output raster, their value will be calculated based on some mathematical function performed on the each pixel of each cell of the input raster. So as you know, sometimes I said cell, sometimes I said pixel, both are correct. For example, as per this figure you can see this is one input raster, and based on this input raster when you perform local operation, that will create a new output raster. In this new output raster, the pixel value will be calculated based on the input raster pixel value. Based on this input raster's pixel value, cell value, in this cell value have to perform some sort of mathematical operation, then the output pixel value will be calculated. So that is the main point, is the mathematical function. Now different types of mathematical function we can perform. Arithmetical function, addition, subtraction, division, multiplication. So for example, in this input raster, if this cell value is 5, now if you perform addition with 3, that means in this output raster this cell pixel value will be 5 plus 3, that should be 8. So in this way every input raster pixel value that can be sum with value 3 by doing arithmetic operation, by doing addition with 3, the output raster every pixel value we can calculate. So not only arithmetic, lot of logarithmic functions like exponential, logarithmic function, trigonometric operation like sine value of a pixel, cos value of a cell, tan. So all such type of trigonometric function also can possible to apply on the input raster every individual cell, and then in the output raster corresponding cells value we can calculate. We can also use square root, square, power. Suppose this pixel this input raster cell value is 5, so after doing square for this output raster pixel value will be 25. Just like this, square root, power, square, all such type of mathematical function we can use and we can generate. For that reason local operations are also called cell by cell operation. Here every cell in the input raster we consider in this input raster every cell have to perform some sort of mathematical operation, then the result will store in the output raster every individual cell. So for that reason this is called local operation with single raster is called cell by cell operation. Arithmetic, logarithmic, trigonometric and power functions are frequently used for local raster operations. These are the common types of function we use. That means we perform mathematical operations on every cell in an input raster. Their value will be changed and those values we can store in a new output raster in their corresponding pixel value. For example, as you can see in this example, a local operation was performed, and by using this local operation, computer convert a slope raster from percentage value to a degree raster here. So the slope of a landscape, you know, the elevation of a terrain, the slope of a terrain, slope can be possible to calculate using percentage or in degree. So in this left hand side, this A image is a input image, and after doing local operation, this B image is the output image. Now how this output image was calculated? In this input image, every pixel contains slope value in percentage. So this 15.2 slope value in percentage is converted to 8.64 degree slope. So 15.2 percentage slope converted to 8.64 degree slope. 16 percentage slope converted to 9.09 degree slope. So that means every cell in this cell performs some sort of mathematical function. This cell value change and that stored in a new output raster. So for that reason I told you this is also people called cell by cell operation. And one common example is the slope of a terrain. If it is present in percentage, that can be possible to change in degree, or vice versa. If slope of a terrain present in degree, that is possible to change into percentage. Now next in this slide we will discuss the local operation with multiple rasters instead of single raster. A common term for local operations with multiple raster we called map algebra, a term that refers to algebraic operations on raster layers. I mean, we will basically perform different types of algebraic operations on different input rasters, plural, not a single raster, and based on this we can create a new output raster. So besides mathematical functions that can be used on individual rasters, other measures that are based on the cell value or their frequencies in the input raster can also be derived and stored on the output raster of a local operation with multiple raster. So not only different types of mathematical functions we apply on input rasters, sometimes we will also consider their frequency, how many pixels have the same value. So such type of statistical operation, frequency, mean, minimum, maximum, range, lot of such type of statistical function we also use, perform computation based on multiple rasters, and finally we create a output raster. So for that reason local operation with multiple rasters are also referred to as compositing, because here multiple raster will combine. So this is also sometimes called compositing or raster overlaying or raster superimposing. That means when multiple raster was superimposed one upon another, or when multiple raster overlay one upon another, so that reason local operation with multiple raster is also called raster compositing, raster overlaying, or raster superimposing. So those three other terminology also use: raster compositing, raster superimposing, raster overlaying. Now let's see some examples so that you can understand how multiple raster will combine and create a new output raster and will perform local operation. For example, you can see this is a one figure where those three raster A, B, C, those three raster are superimposed one upon another. Although just for your understanding purpose I show you top to bottom in this way, but basically those three raster are superimposed one upon another. This is just a abstract view. All those rasters have the same cell size, and also they have the same number of rows, same number of columns. Now in those raster you will see some pixels value are gray instead of any value. That means all those pixels do not have any value. So those pixels or cells are called no data. So in this input raster, in this pixel, no data is there. No data is there. So basically those three raster are superimposed one upon another. Now based on those three superimposed raster we can perform local operation and we prepare a new output raster. The cell value in this output raster D is the mean, average, calculated from three input raster A, B and C by using local operation. So if you consider this upper left corner pixel, in this input raster 5, this one 1, this one 3. So 5, 6, 9. 5 plus 1 plus 3, 9. Divided by 3 raster, 9 divided by 3, 3. So in the output raster, this is the mean value of those 3 raster pixels. The shaded cells have no data, as I told you. In these abstract rasters, those cells have no data. So when those cells have no data, although another raster has a value, but in the output raster it will consider as a no data, because some of the raster do not have any value. That is no data, that is no data. So computer will not at all calculate anything for these 2 pixels. Otherwise this is a basically mean operation. I hope you understand. 3 plus 2 plus 1, 6, divided by 3, 2. 2 plus 7 plus 3, 12, divided by 3, 4. So such type of raster mean, if you want to calculate based on multiple input raster, in this way we can perform this. So here you just see typical summation, then divided by number of raster. By this way we perform raster mean. We calculate raster mean value. Then another picture you just see here, same example, only pixel values are changed. Those 3 ABC input raster, multiple raster, superimpose, local operation, D is a output raster. Now let's see. In this time no mean. The cell value in D is the majority statistics derived from the input 3 raster A, B and C in a local operation. Now you see in this upper left corner pixel value 3, pixel value 1, pixel value 3. So which one is the majority value out of 3? 2 3s, that means output 3. 2 3 3, majority 3. 3 2 2, majority which value? 2. 2 1 2, majority 2. 3 1 1, majority 1. So out of those 3 raster, if it will compare every pixel in every raster, then it will check which one is the major value is there, and by doing this it will calculate majority, and this majority value will store in the output raster. And same like no data. I hope that you understand. So mean, majority statistics we can calculate. This is another raster, something different. In this case we use 2 rasters instead of 3. A and B is the input raster and C is the output result raster. Each cell value in this output C raster represents a unique combination. This is very important point. Unique combination of cell values in A and B. Unique combination means this pixel input raster 3, then in this pixel 3. So 3 3 is a pair unique combination, and it will assign a unique combination, so it will assign a new value 1. 2 2 3. 1 4, where is 1 4? 6. So in these 2 raster it will check every individual pixel in every raster, and whenever it will found a unique combination, that will store by a new value. In this way you see in output raster both cell has the value 4. Why? Because 1 2 combination is 4. Again here 1 2. So the same combination and their value assigned, unique code assigned 4. So in this way, using 2 raster, we can check whether they have a unique combination. If they have a unique combination, in the output raster it will generate, where for every pixel it will assign a new value. So that is another way we can see here. The combination codes and their representation are shown in D box. So this is not a raster, just for your understanding purpose this table was given, so that you can understand what is the unique combination and their unique code. So you can consider those are the slope value, those are the aspect value. So the unique slope, unique aspect combination, 3 degree slope and 3 degree aspect, a unique combination, new value 1. So those sort of example we can set in this way. Okay, but before doing that, I should tell you that lot of application we use raster local operation, either using single raster or using multiple raster. For example, change detection study of land cover rasters of different years. If you have land cover raster for different years for the same area, you can perform change detection study. If you want to perform suitable site selection, a lot of time we perform raster local operation, either based on single raster or based on multiple raster. Then we will go to the next one, that is the neighborhood operation. In neighborhood operations involves a focal cell, involves a central cell and a set of its surrounding cells. So instead of local operation, in neighborhood operation it will consider a central cell or focal cell, and based on this focal cell it will choose surrounding its cells. These surrounding cells are chosen for their distance and or directional relationship to the focal cells. So the surrounding cells we consider based on the distance from the focal cells, or distance and direction from the focal cells, or direction from the focal cells, east, west, north, south, like this, or both distance and direction, east, west, north, west, we can use. Generally, common types of neighborhood we use based on focal cells. If you try to consider its surrounding cells, for surrounding cells neighborhood we consider like rectangle, like circle, like annuluses and wedges. Commonly those four types of neighborhood we consider in neighborhood operation, and based on this neighborhood, based on the focal cells, we calculate this. So this is the example of neighborhood view. This is a rectangle, or you can say square. This is a circular. This is a annulus. This is a wedge shape. So in this case, those cross mark pixel is the focal cell. Focal cell. Based on these focal cells, towards this direction, towards this distance, based on a radius, it calculates surrounding cells. Based on these focal cells to concentric circle, it found the surrounding cells. Surrounding cells are represented by gray color. This is the surrounding cells. So for common neighborhood types, as I told you earlier slide, rectangle, circle, annulus or wedge. This is a rectangle, although you can consider this is a square shape, either called square or rectangle. So in this case, in neighborhood operation, for that reason also sometimes people called focal operation. Instead of neighborhood operation, lot of people prefer to say focal operation. Just like local operation is called compositing, raster superimposing, raster overlaying. So the same way neighborhood operation is also called focal operations. So let's see few examples. As I told you, cell marked with the cross or X is the focal cells. Let's see some of the example. Now you see in this example, this is the input raster A, this is the output raster B. In this output raster B, you may consider the raster size is smaller than the input raster, because here we consider this is the focal cells, and we consider only those 9 pixels. So we calculate this is one focal cells, we consider only 9 focal cells, 1 2 3 4 5 6 7 8 9, and based on these 9 focal cells we calculate the values of those 9 pixels in the output raster. The cell values in B, that means B is the output raster, are the neighborhood means of the shaded cells in A using a 3 by 3 neighborhood. So if you consider this is the focal cells, then its neighborhood is a 3 by 3 window. That means those 4 5 6 7 8, this is the focal cells, its neighborhood is this. If you consider this is the focal cell, neighborhood is this. So according to this, you can see, for example, for this pixel output raster, pixels value calculated 1.56. How it was calculated? It was calculated based on this focal cell, their surrounding cells value. 1 plus 2 plus 2 plus 1 plus 2, 2, 1, 2, 1. So 3, 6, total 9 pixels. Their sum divided by number of pixels 9, and its calculate value 1.56. Now the same way for this focal cell pixel, its value calculated 2. For this focal cell pixel 3, their surrounding pixel value is this. If you perform summation, then divided by 9, its value will be 2.44. So that is called, here we calculate basically neighborhood means. Raster, based on the focal cells, we calculate majority, we calculate the mean, and we create a new output raster. We do not consider here the edges of the input raster pixels. Now another example, same, this is the input raster, this is the output raster. The cell values are the neighborhood range. In this case, neighborhood range statistics of the shaded cells in A using the 3x3 neighborhood. The upper left cell in the output raster B has a cell value 100, which is calculated from 200 minus 100. So this is a focal cells, its value is 200. Now it will check the surrounding pixel value. The lowest value is 100. So 200 minus 100, this is 100. If you consider focal cell 110, surrounding pixels, if you see in this way, this is the highest value 210. So 210 minus 110, 110. So this is called range statistics. In this way, as per your requirement, we can calculate highest value minus lowest value. Once you get, then you will get the result range value, highest minus lowest. So in this way, here neighborhood range statistics calculated for every pixel in the output raster. 70 you check, 160 its surrounding value, whatever is there, if you check, then you will get this. What is this? What is 100? 100 exactly 100, and you will see here 70 was calculated. Highest value, which one is the highest value? Here 170. Which one is the lowest value? 100. So 170 minus 100, that is 70 is there. Now another one we just show you here, neighborhood majority in a 3x3 window. This pixel 2, majority pixel 2, 2, 2, 2, 2, except those three value is 3. For example, you can see here in this output raster, this pixel value is 2 because there are 5 2's based on focal cell. In the surrounding pixels, 5 cells are there, their value is 2, 1, 2, 3, 4, 5, and the 4th cell's values are there 1. 5 2s and 4 1s. So majority which one? 2. So 2. So in this way we can also use neighborhood mean, neighborhood range, many more statistical and mathematical operation we can use, and based on this we can create a output raster. Lot of application where we perform neighborhood operations. For example, two common application of neighborhood operations are image age enhancement. If you want to increase the age of the image entity, and for image smoothing purpose we also use raster neighborhood operation. Image age enhancement and image smoothing operation purpose we use it. Okay, so local, focal, then we should discuss the zonal operation. In zonal operations, instead of focal cells or cell by cell operation, it will use a group of cells, and all those group of cells have the same value, and those group of cells which have a same value is called zone. These groups are called zones. Zones may be contiguous or non-contiguous. If you consider soil type zone, soil mapping, in the soil mapping this zone is soil type zone is the typical example of contiguous zone. If you consider the land use, if you see the land use map, you can see somewhere agricultural land is there, again in different location also agricultural land is there. So this is the example of non-contiguous zone. So zone may be contiguous, zone may be non-contiguous. As I told you, example of soil zone, soil map, whatever the zone you found, this is a typical contiguous zone. Example of land use land cover map, the zone that you found, this is a example of non-contiguous zone. A zonal operation may work with a single raster or multiple raster, two rasters, either based on single raster we can perform zonal operation, or based on two rasters. Given a single raster, when you perform zonal operation basically measure the geometry of each zone. Measure the geometry of each zone in the raster. By measuring geometry, it will calculate area, perimeter, thickness, and the centroid of the zone. But when you use two rasters in a zonal operation, one raster we will consider as an input raster where we will perform computation, and another raster we will consider as a zonal raster. A zonal operation produces an output raster, just like focal and the local operation, which summarizes the cell values in the input raster for each zone in the zonal raster. So based on zone in the zonal raster, we will consider the input raster, we will find out all the pixels that are present in a particular zone. Their summary statistics we will calculate. Let's see, this is an example of zonal operation with a single raster. In this raster, this is a one zone, this is another zone. So when you perform zonal operation on a single raster, it will calculate every raster zone centroid. It will calculate their area, for example in square kilometer. It will calculate their perimeter of every zone in kilometer, and it will calculate their thickness. What is the maximum from the centroid? If you draw a circle in such a way that will touch the boundary, this circle radius is called thickness. So perimeter and thickness we can calculate using kilometer or meter. Area should be square kilometer or square meter. Thickness and centroid for two large watershed. So this is one watershed zone. If you consider another, their thickness, their zone, centroid we can easily calculate using zonal operation. Centroid of each zone is marked with the cross. Then this time we perform zonal operation with two rasters. This is a input raster, this is a zone. This is a zone 1 because all the group of pixels have the same value. Zone 2, zone 3. So this raster and this raster are superimposed. Now based on zone, all those pixels are present in the same zone, that is zone 1, zone 2, zone 3. Now we can perform zonal mean. So in the zone 1, whatever the pixels are there, we can calculate their mean value, and that will assigned in a new raster, output raster. All the pixels have the same mean value. You see 2 plus 1 plus 1 plus 2 plus 3 plus 4, then divided by 6, you will get 2.17. 112243 for zone 1. Zonal mean we can calculate in this way. So the same way for zone 2, 2 plus 5 plus 1 plus 1 divided by 4, you will get this one. So this is the example of zonal operations, either based on single raster or based on two raster. One is input raster, another one zone raster. If we choose, then we can perform zonal operation. Zonal operation is useful in studies of landscape ecology, for example, or if you want to compute the topographic characteristics of different soil texture on the land surface. For example, topographic characteristics on the land surface, if you want to calculate, then we can also use zonal operation. Along with, if you want to perform study the landscape ecology, we also most of the time perform zonal operations. Then we will consider the physical distance measure operations, where we will measure the distance. In this case, you will see physical distance measure the straight line or Euclidean distance, which is called. It calculates straight line distances away from cells designated as a source cells. Whenever we will perform physical distance raster measure operation, physical distance measure operation on raster, there should be some source cells or cell. Based on this, we will perform straight line distance or Euclidean distance measurement. Suppose if you consider this is a source cell, from this cell, if you want to measure the distance of this cell, the straight line distance, and the physical distance measurement we perform based from the cell center to another cell center, not the cell edge. A straight line distance is measured from a cell center to another cell center. For example, to get the distance between cell 1 from cell 1 means number 1 column, number 1 row, to the cell 3, that means cell column number 3, row number 3. So the cell address represented by 11 and 33. If you calculate the distance between those two cells center to center, we can use this formula. What is the cell size, cell width and height, that should be same, into square root of 3 minus 1, 3 as I told you, column number minus 1 is the another cell's column number, plus 3 is the row number, minus another cell's row number, minus 1 square. So for example, if you consider the cell size is 30 meter, imagine this is 30, this is 30. So what should be the distance from this cell center to this cell center? It should be exactly 84.84 meters. If we consider cell size 30 meter, so if you 30 into this, actually it will measure the distance in meter, and it should be 84.84 meter. So in this way we can perform physical distance measurement. So this is a one example. This is a stream network, or you can say river tributaries. Based on these river tributaries, this is the physical distance measurement performed by computer. As you can see in this figure, this is one distance, another, and that is going on the distance measure. This is the source cells. Here source cells are the river tributaries or stream network. Now then we will discuss the allocation and direction, which is related to physical distance. Allocation produces a raster in which the pixel value corresponds to the closest source cell for the cells. It will consider the source cell or cells. Based on this, every other cell's distance it will calculate, and according to this, nearest source cells wise the cell's value will allocate. Direction produces a raster in which the cell value corresponds to the direction in degree that the cell is from the closest source cell. These two are very important point, but for understanding purpose I am first showing you this figure. So the A is the physical distance raster, B is the allocation raster, C is the direction raster. This, now this. Now let me explain. Now based on the source cells denoted here as 1 and 2. So this is the source cells, cell 1, cell 2. We identify source 1, source 2, and based on this source 1 and 2, this is the physical distance measured. Physical distance measures in cell units from each cell to the corresponding source cell. So from this pixel center to this pixel center distance is 1. Why 1? Here we consider pixel width and height is 1. If you consider pixel width and height is 1, from source cell center to this 1, this 2, this 1, from this 1, 2, 3 cell unit 1. This is 1.4. Why? Because the distance from this cell center to this is root 2, and as all of you know, the value of root 2 is 1.414. So in short, 1.4. Now here you will see this pixel was represented in gray color, as you can see. Okay, so why this one is the gray color, I hope you understand. That means in this cell, from this cell, the distance to this source number 2 and to distance to this source number 1 is the same, 2.2 meter. So from this cell center point to the source 1 center point, and source 2 center point distance is same, 2.2. So for your understanding purpose, in this figure we show it in gray color. Same distance from both the source point. So this is the way the allocation raster generated. And now this is the B raster, this is the allocation raster. And allocation raster, each cell to the closest cells. So according to their distance, all those pixels are closest to 1, so their value will be 1. All those pixels, they are closest to 2, so their value is 2. Now you can argue with me, sir, what should happen with this particular cell, because this cell's distance to source 1 and 2 both are same. That means these cells can be allocated either in source 2, or it is also can be allocated to source 1, any one. So it is your choice, either we can allocate it into 2 or in 1. It can be allocated, but all other cells, they can only allocate either in near to 2 or near to 1, near to 1, near to 2. Only for this, either 2 or 1, although as per this example we assigned it in the source 1, so we allocate it in source 1. And the third one is there, this is called the direction raster, where every cell's value is calculated as a degree from each cell to the closest source cell, direction from each cell to the closest source cell. Now you have to remember that the direction values are based on the compass direction. That means in compass direction, 90 degree means to the east, 180 degree to the south, 270 degree to the west, and the 360 degree to the north. Here 0 is reserved for the source cell. So those two source cells, their value we reserved for 0. So for this one, as you can see, this cell value is 270 degree. 270 degree, that means from this source cell, from these cells to the source cells, direction is towards west. This one is 90 towards east, west, east. So every cell's direction towards the source cell, from this cell to the source cell direction is northeast. From this cell, totally north. From these cells, totally northwest. So this way, from these cells, totally you can see also in the northwest. For this one, 180 degree, that means towards south. That means from these cells towards source 1, towards this direction. But here you can see for this gray pixel, where we consider 243 degree. 243 degree means this one is towards southwest. That means it was allocated to 1, so its direction towards southwest. So 243 degree we consider. So in this way it was calculated. I hope that you understand here. Okay, so that is the allocation, physical distance, allocation and direction raster. Then we can also perform raster clipping. This is the input raster. It can be clipped by either another raster or based on some vector data we can clip it. A analysis mask is used to clip the input raster. So based on this analysis mask, this input raster was clipped. The output raster C, which has the same area extent of the analysis mask. So based on such type of analysis mask, we can also perform such type of raster clipping. Then we will discuss the raster aggregate. This is basically generate lower resolution raster. This is the input raster, and from this input raster we generate a lower resolution output raster B. This operation uses a mean statistics, mean of those 4 pixels 2 by 2 window, 3, 4, 5, 8 divided by 4, so 2. So those 4 pixel was combined, create a lower resolution large size pixel. Their value assigned based on the mean statistics. So the same one, those 4 pixels value, based on those value, mean value calculated and combined, create a lower resolution raster. So in this way, higher resolution raster to lower resolution raster, lot of time we prepare using the raster aggregate operation. And this one, this one is the last one is there. This is the region group operation. Whenever we will found the connected cells, this is the input raster, this is the output raster. Those 4 ones are connected, it was assigned in the output raster 1. Those 3, 4 are connected, they have the same value, assigned a new value 2. Those 4 ones are connected, so assigned a new value 3. Those 2 same value connected, assign new value 4, 3, 4. So in this way, each cell in the output B has a unique number that identifies the connected region to which it belongs to in the input A. For example, the connected region that has the same cell value of 3 in A, you see those have the same cells have the same cell value, they are connected. In the output raster, their cell value we computer generate 4. So those sort of unique combination it will create using region grouping. Generally we perform such type of raster operations here in GIS software. So that's all regarding the raster analysis technique. Thank you.